In the domain of science and immense enigmas, the topic of what came before the Big Bang has stirred discussions and captivated thinkers for ages. This deep inquiry goes beyond merely examining how we interpret the cosmos. It pushes the absolute boundaries of human comprehension. Picture standing at the brink of existence, gazing into the vast unknown, wondering what existed before the universe as we know it was created. The Big Bang occurred, signaling the onset of time, space, and everything familiar to us. But was there a moment before this event? Could there have been silence, a state of complete stillness, before the cosmic unfolding began? And if so, was it truly empty, or did something even more extraordinary precede time itself? As we delve deeper into this question, science leads us on a voyage beyond the birth of the universe into ideas that stretch the limits of our understanding. Brian Cox, a well-known physicist celebrated for exploring the marvels of the universe, proposes that it's possible the unexpected existed before the Big Bang. He challenges us to rethink our notions of reality and existence. In this exploration, we'll break down the science, the hypotheses, and the mesmerizing mysteries that could help explain what came before everything we know. We'll consider theories involving quantum shifts caused by inflationary expansion, dark energy, and even parallel universes. The revelations may astonish you, but they also have the power to reshape how we know where we fit in the universe. Prepare to venture into a realm beyond imagination and empirical science, a space where the unknown still weaves through the darkness, leaving scientists amazed and at times unsettled. Let's examine what may have preceded the Big Bang and why such ideas disrupt everything we assume to be true. To understand what might have come before the Big Bang, we first need to thoroughly examine what the Big Bang actually was. Scientists describe the Big Bang as the moment when the entire universe, incredibly dense and scorching hot, quickly expanded to begin the formation of matter, energy, and the fundamental forces. When we gaze into the night sky, we observe evidence of this. Galaxies with a fiery origin, moving outward from a common point in their early history. But why did this happen, and was there a phase before this intense expansion? According to the inflation theory, there indeed was a before, and it was far from tranquil or empty. Cosmic inflation posits that before the Big Bang, the universe shuddered, cold, sparse, and relatively structureless, resembling a vast vacuum. Yet this vacuum wasn't completely void. It contained an enormous quantity of energy that drove the swift expansion of space. This expansion, known as inflation, was so rapid that it laid the foundation for everything that followed. A phase of space growing at unimaginable speeds until the process slowed down to allow the energy to change into particles, matter, and forces, ushering in what we perceive as the Big Bang. But what was this energy? Why did it cause the universe to expand so suddenly? And what made it stop? Experts believe that this boundless inflation may have produced patches of the cosmos, each undergoing its own version of a Big Bang. Envision a limitless sheet stretching out, forming tiny bubbles here and there, each bubble representing a separate universe, including ours. This concept, called the inflationary multiverse, proposes the existence of countless Big Bangs and an infinite array of universes. Ours is just one among many. These staggering possibilities put the very foundation of cosmology to the test and force us to ask, what else lies beyond? The notion of absolute emptiness before the Big Bang remains highly speculative and, according to current physics, not practically apparent. Even when we strip away all matter, energy, and radiation, true nothingness still wouldn't exist. Our universe is permeated by dark matter, dark energy, quantum fields, and invisible forces that form an inescapable fabric of somethingness, even in the most empty scenarios. Even if we imagined removing all these components and were left with a barren void, new energy would still emerge from this seeming nothing. This alone confounds scientists, implying that genuine emptiness may be unattainable within the framework of our infinite universe. Space has inherent attributes, physical laws, and constants that prevent it from ever being truly vacant. Crafting a space devoid of particles, radiation, and all energy, even in this hypothetical vacuum, quantum fields and physical constants would continue to exist. This suggests that what we call nothing still has structure. For example, there's a phenomenon known as zero-point energy, which describes the lowest energy state of quantum fields. In this condition, particles can still momentarily appear and disappear, creating a ghostly hum of activity when there ought to be stillness. This contradicts our classical idea of a void and implies that even before the Big Bang, there was something we are only starting to comprehend. One of the most amazing concepts in present cosmology is the prospect of endless inflation. If inflation birthed our universe, it might continue to generate new universes indefinitely. Brian Cox describes a boundless, inflationary multiverse where universes are constantly forming and expanding. Imagine each Big Bang as a spark igniting another cosmos, while inflation continues to spawn many others in faraway regions. This never-ending cycle introduces the concept of a fractal universe, where every new universe could give rise to its own Big Bang. Each one would be independent, unaffected by the rest due to the rapid separation of expanding space. For physicists, this notion is thrilling yet disturbing. It suggests a multiverse that has no beginning or end and positions our universe as just one small piece in a vast, ever-growing cosmic network. What if there's no before or after, only an infinite, eternal cycle of growth and decay? Our understanding of nothingness changes dramatically when we examine it through the lens of quantum field theory. This theory suggests the universe is not merely a collection of matter drifting through space but a vibrant lattice of energy fields that interact and result in everything we observe. These fields are akin to invisible oceans, whose ripples are particles that behave like waves. Even in their lowest energy state, the vacuum, fields are dynamic. Particles can flash into existence briefly, gain energy, then vanish, leaving behind a whisper of their existence. These virtual particles challenge the notion of a true vacuum. Imagine a universe stripped of matter and radiation. Would that be pure nothingness? According to quantum theory, there is no emptiness. Fields would persist, fluctuating and occasionally producing short-lived particles. This ceaseless activity in apparent nothingness tells us, the universe never reaches absolute zero. This revelation, that even in the absence of matter and energy, a hidden dynamism persists, has profound implications for how we interpret the concept of before. If a true vacuum never existed, then the pre-Big Bang state may not have been nothing, but rather a different kind of something, a primordial quantum landscape governed by laws we are only beginning to grasp. Some theories propose that the universe arose from a quantum fluctuation, a random, temporary change in the energy of empty space. These fluctuations, though minuscule, could create conditions stable enough to give birth to an entire universe. In this framework, the Big Bang wasn't the beginning of everything. It was the beginning of our observable universe, emerging from a deeper quantum reality. This brings us to another provocative idea, the concept of cyclic cosmology. In such models, the universe undergoes infinite cycles of birth, expansion, collapse, and rebirth. Instead of one singular Big Bang, there may have been countless cosmic epochs, each following the demise of the previous one. The current expansion could eventually reverse, leading to a big crunch, followed by another Big Bang, and so on, endlessly. These models challenge our linear understanding of time. What we perceive as a beginning might simply be a transitional phase in an eternal cycle. In this view, asking what came before the Big Bang is like asking what came before the beginning of a circle. The question itself assumes a starting point that may not exist. Philosophically, these ideas blur the line between science and metaphysics. They force us to confront the limitations of language, perception, and even logic. How do you describe before time, when time is a condition that only began with the Big Bang? Still, scientists continue to probe. Advanced instruments like the James Webb Space Telescope and high-energy particle colliders search for traces of what may have occurred in the universe's earliest fractions of a second. These tools, along with mathematical models, may one day offer concrete clues, tiny scars left in the cosmic microwave background, or subtle anomalies in the behavior of particles, that point to a pre-Big Bang reality. In the meantime, the question remains one of the most tantalizing frontiers of human thought. Whether we find definitive answers or merely better questions, the pursuit itself expands our understanding not just of the cosmos, but of our place within it. In contemplating the unimaginable, the moment before time, space, and being, we are reminded that science is not only a tool for understanding the world, but also a mirror reflecting our deepest existential curiosity. The void, it seems, may not be empty at all, but full of hidden truths waiting to be revealed. Instead, it bubbles with hidden energy that defies emptiness. This insight raises the issue of whether energy fields spawn particles, and particles create matter. Could the universe have emerged from this so-called nothing? Dark energy, the enigmatic force accountable for the accelerating expansion of the universe, could be a remnant from before the Big Bang. The fact that dark energy still exists may hint at an ancient field predating our cosmos. Some theories propose that, in a more potent form, dark energy may have triggered inflation and driven the rapid expansion of space. If dark energy persists even when there isn't matter, then perhaps it shaped the conditions that allowed our universe to come into being. Could it be the hidden hand behind inflation, or even the original spark? As we entertain this idea, dark energy moves from being a passive force to an aspiring architect of existence, holding secrets about the multiverse. Another alternative is found in cyclic cosmology, the idea that the universe is caught in an infinite loop of creation, destruction, and rebirth. Here, the Big Bang is not a single occurrence but one phase in an eternal sequence of expansion and collapse. Our universe may have emerged from the remnants of a previous one, collapsing and re-emerging over and over again. If this theory is accurate, there may never have been a first universe. Instead, existence is cyclical, constantly renewing itself. This model also alters our concept of time, suggesting it may be circular, not linear. A universe born, evolving, dying, and reawakening endlessly would have no true beginning. Gravitational waves, ripples in space created by major events, provide another avenue for understanding pre-Big Bang conditions. If early gravitational waves were detected, they might reveal echoes from before the Big Bang itself. These signals could preserve information about a past cosmic state and serve as evidence that something existed before our universe. Such a discovery would be groundbreaking, conceivably proving theories that point to a pre-Big Bang reality. As we pursue these questions, we explore ideas that push the boundaries of logic, time, and space. One of the most ambitious is quantum gravity, which aims to unite Einstein's theories and quantum mechanics in general relativity into one theory. This union could revolutionize our understanding of what preceded the Big Bang. According to quantum gravity, space and time might not be smooth, but rather comprise tiny units at the Planck scale. These discrete structures could have generated the spacetime fabric we know today. In this model, what we perceive as continuous space and time only emerged after quantum fluctuations shaped them from something more fundamentally radical. This different framework implies that, before the Big Bang, reality may not have included time or space as we understand it. The string landscape that comes from string theory adds another layer. It suggests our universe is one of many, each defined by different physical constants and laws. Tiny vibrating strings underlie all particles, and each arrangement of these strings creates a different universe. This framework allows for each of the innumerable possible universes to begin with its own Big Bang and evolve independently. This implies we're not alone in the cosmos, but one drop in a vast ocean of realities. Some theorists propose that our universe might have originated from a black hole in another universe. The singularity at a black hole's center, where density becomes infinite, could theoretically spawn a new universe. The Big Bang may, in fact, be the outcome of such an event. This idea suggests that black holes may serve as cosmic wombs, creating new realities beyond their event horizons. If true, each black hole could be a portal to another universe. Finally, the very concept of time may be misleading. If time began with the Big Bang, then asking what came before is meaningless. There would have been no before without time itself. Some cosmologists propose that time emerged from a primordial state, a chaotic quantum event where past, present, and future were undefined. Others return to cyclic time, where the universe eternally oscillates between expansion and contraction. In this vision, the Big Bang is just one cycle among countless others. No beginning, no end, only a rhythm of cosmic breathing. Some theories even envision a primordial soup of particles and fields, quarks, leptons, bosons, all churning in a high-energy state before expansion. It's possible that building blocks existed in a quantum foam, constantly flickering in and out of existence due to the uncertainty principle. This soup could provide a bridge to the time before time. In the end, the question of what existed before the Big Bang remains one of the deepest mysteries of modern science. As our understanding of physics, space, and time advances, so too do our theories, each more intricate than the last. While we may never have a definitive answer, the pursuit of this mystery drives humanity forward, fueling our innate desire to explore the unknown. This relentless curiosity, the desire to peer beyond the veil of the observable, defines our species. The very act of questioning what came before the Big Bang is a testament to our refusal to accept limits, even those seemingly imposed by nature itself. We craft new mathematics, reimagine the laws of physics, and build ever more sensitive instruments, not merely to understand our origins, but to challenge the notion that some truths are forever beyond reach. In probing the moments before time, we also reflect inward. These cosmic questions become mirrors, revealing the profound connection between consciousness and the cosmos. Why do we yearn to understand the beginning? Perhaps it is because, deep down, we sense that the universe and our awareness of it are entwined. That in tracing the birth of space and time, we are, in some way, searching for the origin of meaning itself. Philosophers, too, have entered this grand arena, proposing that existence might be a necessary condition, that something must exist because non-existence is inherently unstable. From this perspective, the void is not empty, but seething with the potential to become. The universe, then, is not an accident but an inevitability, the only possible outcome of reality's inherent need to be. Meanwhile, emerging fields like quantum cosmology hint at a self-creating universe. In these models, the cosmos could arise from a quantum fluctuation, uncaused and spontaneous, like a wave rising from a still ocean. The uncertainty principle allows energy to appear briefly from nothing, and given the right conditions, such a fluctuation could blossom into everything we see today. In this view, the Big Bang is not a singularity but a transition, from a quantum potential to a classical reality. Yet even as these theories grow bolder, they remain tethered to a central truth: we don't know. Not yet. And that is perhaps the most exciting part. Our ignorance is not a void, but a frontier. Every time we ask what came before the Big Bang, we stretch that frontier further, daring to imagine what lies beyond the limits of time, space, and even comprehension. And maybe, just maybe, the answer isn't a place or an event, but a new way of thinking. A transformation in how we perceive reality itself.